Welcome back, everyone. So today we'll get started with the very last lecture for this course. And like I said before, this is one of my most favorite topics. Uh, this is on memory design. Okay, and we will learn about a few mainstream memories, and towards the end of this lecture, we will talk about some emerging memory technologies, which are very cutting edge, I should say. So without further ado, let's get started. The first slide will give you some idea about the seriousness or delicacy of data storage in modern day electronics. So on the left, you see a memory device. This was known as core rope memory. I mean, I hope you can easily see that they essentially look like ropes, bundled together, right? That's exactly how these memories used to be made. And by using these structures, you were able to store magnetic memory bits like 0 and 1. These are binary data, but you could store them using magnetic fields. This particular memory device was used in the Apollo mission, which took us to the moon. Okay, and the storage capability of this memory technology was 72 kilobits and kilobytes. And if you think about it, nowadays you wouldn't be even able to store a single image within that much storage, right? So we are living in a data-driven world. We are living in an age where digital data is being created in an unprecedented proportion. So the importance for memory devices were always important, but the importance of memory devices have drastically increased within this decade and the previous one. Within the last 20 years, there has been unimaginable growth in digital data across the world. So the device design and memory circuit design has become more important for anyone who wants to dominate in the field of electronics. Now, the figures on the right is intended for a very simple purpose, to show you how important even a single bit of data is. By the way, we are living in the digital electronics era. uh, Information is digitized. That means in everything that you can think of will be represented in terms of streams of binary digits, zeros and ones. Okay, even the letters. For example, let's take these two words, cat and bat, and as you can see, they only differ in terms of just a single letter, C and B, right? And there are ASCII codes. I think you guys all know about them. You can represent each and every letter using a stream of specific binary, right? And the binary that represents C and the binary that represents B differs by just a single bit, as you can clearly see here from here. That means for some reason, if you have a failure to store one bit, or if you have a mismatch, or if you have maybe an accidental data flip in just one bit in your memory devices, that can drastically change a lot of things. For this simple example, cat can be converted to a bat, but that's not maybe too much of a problem. But imagine uh, if numbers start changing, then maybe think about a bank which is trying to keep track of the amount of money in an account, right? Maybe if you add one extra zero, or if you get rid of 10, million can become maybe thousand, right? Just imagine that. So the point is, it is important for us to make sure each and every binary bit that we store in memory devices and circuits are stored in a secured fashion. They are reliable. They can hold on to the stored data for a significant amount of time, as much as is required by the application. And then you can reliably read the binary bit out of it. That means when you try to read whether it was storing zero or storing one, the memory device, right? If you misread for some reason, then you have the exact same effect of a misstorage. Cat can be read as bat, as you see. So we need to have reliable reading and reliable writing, and reliable hold or storage in a memory device. So having said that, let's jump into the classification of different memories. There are some memories which falls under the category of read-write memory, which allow you to read and write from it. And there are memories that are just read-only. You cannot write into it. These are just programmed once in their life, and they will be so forever. Uh, like, for example, uh, ma mask programmed programmable ROM. You might remember FPGA and field programmable gate array and mask programmable gate array. We talked about these two in the previous lecture, right? So when you do so, you actually make changes in the fabrication steps. And once you have programmed something in these memory devices, there is no changing of those data. That's why these are read only. But there are very few read only memories that are used in the digital electronic hierarchy. Most of these are read write capable. So read write memories can be categorized into two branches: random access and non-random access. Meaning, we will talk about this SRAM and DRAM, by the way. We'll get there, but let's start with non-random access. That means you cannot randomly access any particular bit at a time. For example, a FIFO memory, like first in, first out, last in, first out, the name tells you, or shift register, the name tells you you can only access specific bits. Shift register, we talked about shift register design in the multiplier lecture, right? You noticed how you can shift one bit at a time, and depending on how many bits you're shifting, you can access that many number of bits at a time. CAM, content addressable memory, all of these fall under the category of non-random access. You cannot just randomly decide to read memory number 127. No, right? You have to maintain some rules depending on the algorithm that you're using. But random access memories are the most versatile. As the name suggests, you can randomly access any of them. You can choose to write or read from any memory cell in the array. And that's the best part about random access. And we will take some significant time to talk about random access memories, both of them, SRAM and DRAM, because these are the mainstream memories that we use. So the computers that we are using, the video that you're looking at right now, the everything is being driven by this combination of SRAM and DRAM. The processor is taking data from the DRAM and putting data from the DRAM and using the SRAM for temporary storage and processing. Okay, so these SRAM and DRAMs in my laptop and in your laptops, in all of your devices, are in play, even as we speak. Okay, so these are mainstream memories. And then there are non-volatile read-write memories, which are gaining immense attention right now. These are typically storage class memory. Think about portable hard drives or flash drives that you use to transfer data from one place to the other, right? Even when you take it out of the port and store it for a while, your data still remains intact. Okay, that's called retention. These devices can retain the stored data. Flash memory, we will talk about that briefly. EPROM, electrically erasable programmable ROM, E2PROM, or electrically programmable ROM. These are, typical mainstream kind of things, mainstream non-volatile, but these are often used in microcontrollers, not that much into modern day processors. But flash memory is ubiquitous. We all use flash memories nowadays. Uh, Anyways, without further ado, without talking too much about the names, let's dive into the descriptions. So before we start looking at individual memory cells, let's look at a high level picture of the memory architecture. Okay. So memory cells, let me use, that's okay. Memory cells are arranged in different arrays like this. They, the reason why we arrange memory cells in array in an organized fashion is because we can assign addresses to these memory cells. For example, this cell will be in second row, second column. So 2, 2. This cell will be in second row, third column. So if you arrange memory cells in an organized fashion in an array, then it allows us to decide which one to access specifically, right? Unlike logic could be randomly distributed. You just care about the connections. You don't need to access each and every individual logic in a digital processor, say. But for memory, each and every cell matters. You need to be able to address individual cells uniquely. That's why the memories are always organized in a regular fashion. And you might remember we looked at the images of processors, real processors, and you noticed that the memory blocks are very organized and the logic blocks were more like rat's nest, right? We talked about that. They are random, they are automatically generated, but the memories are carefully designed to make sure it's regular and you have addresses. So what you see here on the left is different rows of the memory, and the rows are often called word, typically made of 16 cells or 16 bits. say word 0, word 1, word 2. These are essentially rows. Okay. And what you don't see here, but they're there, that is, you also have different columns. So cells have a unique row and a unique column. Okay. These intersections will matter. Now, the point that I'm trying to make here is that, say you want to access word number 1 or word number something, 7, 10, whatever. Okay. You need select signals to first select that row and then go inside a specific memory cell and bring that out, read or write into it, say. But if you start using separate select signals, you'll have to route a lot of interconnects. Maybe imagine a 256 by 256 array. Then you will need 256 such control signals to control them, which is a lot, and it will take up a lot of area, by the way. Remember, for memory design, density matters. The more memory cells that you can fit into an array, the more data you can store. Imagine one particular cell will store 1 bit, right? Just imagine this simple thing. Just to store a C, you need how many? 1, 2, 3, 4, 5, 6, 7, 8. 8 memory cells just to store one letter, right? You can easily appreciate the amount of memory cells we'll need to store something like a complete video file, say. Okay. So when you have that many control signals, individual control signals, it becomes infeasible for us to make larger arrays. So what we do here is we use decoders. Decoders, we haven't talked, about decoders too much. These are typically taught in the digital design courses, decoders and encoders, stuff like that. What they will do is they will take in, a reduced number of inputs, say 4 bits. With 4 bits you can create different combination like 0000, 0001, 0010, 0011, blah blah blah, right? You can actually create 16 different combinations using 4 bits. Using 3 bits you can create 8 different combinations. So depending on how these bits are organized, whether you have 0000 or 0001, you can choose these 16 different rows. That means you can reduce the need to route 16 control signal to 4. So you can, exponentially reduce. If you need 32, you'll need just 5 inputs and you can have 32 lines. You can control 32 lines using just 5 control bits. Okay, that's why the decoders are used. Decoders can choose, maybe say if you have 0000 in this combination, it will choose the first row, and then 0001 it will choose the second row, something like that. Okay. So we have, these are called row decoders because these are selecting the rows. We will also see column decoders and we will gradually talk about it. The point that I wanted to make here is that using decoders logarithmically reduce the number of control signals, input bits that you need. Now here comes the full picture, and you see this is a standalone storage cell, just one single cell, and you want to access that. So you first have to access the word or the row, and then you have to access the corresponding bit. So these are called bit line and word line. Okay, and you have row decoders that I've just talked about. And then, by the way, when you access the bit line, you access it either to write into it or to read from it. To read from a memory cell, we use sense amplifiers. I will talk about those things briefly in this lecture, but for now, just imagine this is a simple black box, okay, which allows us to sense the stored data. That's why the name, sense amplifier, and drivers and peripherals, blah, blah, blah. After that, you also have column decoder. So similar to the row, you also have to make sure you can individually access each and every one of these columns, and you need another decoder for that. So you first use your row decoder to select a row, and then you use your column decoder to select a column, and the intersection between these two will give you the exact memory cell that you want to access. Okay, so 2 decoders, row and column decoders are used. And by the way, this is an even higher level picture of the memory array. We don't have all the bits connected in just one particular block. There are so many reasons for it. I mean, here is one idea. Imagine the memory cell. Let me just clear it up a little bit. So the memory cell that is at this corner, the very first memory cell, will be closer from the voltage source, right? The voltage source that you're using to read and write. And then imagine another memory cell like this. This is farther away from the voltage source. And this memory cell will not have as much voltage as input. It will have a degraded input. The reason is, when you imagine you have different uh, nodes that will appear before the last memory cell, and you have a voltage source right here, say, right, you have a voltage source, and then there will be resistive drops across the interconnect. So you will gradually degrade the voltage. So you start with 1 volt, then you'll have zero 0.9 volt, you have zero 0.8 volt, and so on. So gradually it will degrade. So the larger the array is, the more degradation you will experience. So the cells that are farther away from the array, from the voltage sources, like read and write voltage sources, they will not see as much read or write voltage. Okay. And then you can have failure in terms of programmability. You might not be, you are trying to write one, but it will fail, right? So what we do here is to count. This is just one reason, by the way. There are many other reasons. This is a very simple, relatable reason, I hope. Because you learned about VDD degradation, right? You learned about how resistances in the interconnect degrades the voltage. We talked about that in one of the lectures. So the fact is, we don't use a huge array. We divide it into smaller chunks, and then we first select a chunk like a block, and then within the block we select a row and a column, and that's exactly what you see. This is block 0 and blah blah blah, so many different blocks. You first select a block, and that's what you see here, block address. You either select this one or this one or this one. Say we have selected this one, that's why it's gray. We select this block. Within that block you have a row decoder and we have a column decoder, and that row decoder and column decoder then selects a row and a column, and the intersection between these two will be the cell that you are accessing. Okay, that's how we access. We divide the overall array into smaller chunks for better addressability. Okay, please feel free to interrupt me if you have any questions. Okay, I don't know whether I'm going too fast or too slow. Just let me know if I'm too fast. Okay, now with that picture in mind, now we are ready to talk about some specific memory technologies, namely SRAM and DRAM. uh, SRAM is known as static random access memory, or static RAM, and I will explain the name, why it is static. And dynamic, as the name suggests, is dynamic, right? We will talk about the differences there. Uh, Now, I want to just highlight these few points. SRAM is typically large. You will appreciate when we talk about it. It has 6 transistors. One transistor is too much, by the way. For example, in DRAM, we just have one transistor. We might have up to 3 transistors, depending on the type of the DRAM. We will talk about both, but not even close, right? SRAM will have at least double, uh, the transistors compared to the DRAM. So that's the problem. But the good thing about SRAM is they are fast, like they are crazy fast. We haven't been able to create another memory device as fast as SRAM. That's the reason why, even with having that many transistors, they are still used in modern technologies. Okay, DRAM obviously opposite. They tend to be slower, but they have some added benefit. The problems that DRAMs have is periodic refresh. We will talk about all of this. I'm just reading it up loud, but we will discuss all these problems. And in SRAM, data is stored as long as the supply is supplied, like voltage is supplied. As soon as you remove the applied voltage, it will lose all the stored data. Just keep that in mind. That's not the case for a flash drive or a pen drive, right? Whatever you want to call it. When you remove it from the USB port, it still holds on to the stored data. It has lost power, by the way, but it will still hold on to the stored data because it's non-volatile. SRAMs are volatile memory. Volatile memories are the ones that lose the stored data as soon as the power goes out. Okay, just keep that in mind. And differential, we will talk about what that means. So these are just key points that we need to keep in mind about SRAM and DRAM, and all of this will make more sense once we learn about the structures. So let's start from the simple one, the DRAM, which has just one transistor. So you have one transistor and a capacitor. Let me tell you something. The fundamental concept about storing data is somehow managing two different states, physical states. Imagine you have a block which can exist in two different resistance levels. It can either be programmed into a low resistance or a high resistance, say, somehow. I don't know how. There are ways. So you can use the low resistance to represent 1 and high resistance to represent 0. And then this will qualify as a memory device. Imagine a capacitor. You can either charge it up or you can discharge it, right? When it is charged, you can represent logic 1 with it. Discharged, you can represent logic 0 with it. Okay? Simple concept. Any two states. Uh, there are memories where we will talk about them. You have two magnetic layers, layer 1 and layer 2. And they have different magnetization. If they have the same magnetization or parallel magnetization, we can represent that with logic 1. If they have anti-parallel magnetization, we can use that to represent logic 0. Okay, so I hope you appreciate that whenever we find two levels, two physically stable levels, uh, we can use these two levels to represent logic 0 and logic 1. There are two things to keep in mind. We should be able to program it at will. Like if we want to flip it to the other case, we should be able to do it. That's what programmability demands. Next, we should be able to sense what is being stored. For example, the very first thing that I told you, LR, low resistance state and high resistance state, right? We have to somehow somehow sense how much resistance this thing has, so that we know whether it is storing 0 or 1. So you have to be able to sense that, and you have to be able to change that at will. That is the reason. But at the same time, it shouldn't automatically change on its own. Otherwise, you write some data into it and it automatically keeps changing. It's not useful anymore. Okay, so all of these things are fundamental concepts about memory devices. Now, with that idea in mind, a DRAM is a very simple memory cell which stores the data in a capacitor. When the capacitor is charged, as I told you, it could be treated as logic 1. When it is discharged, logic 0. The transistor that you have here is only there to allow access to the capacitor. You can selectively charge it up or discharge it or sense what is being stored using this transistor. And here is how you do it. Don't worry about this text. Once I explain this, you can read it up, and I hope things will make sense. Now, this is the word line, this is the bit line, and I hope you know by now what word line means, right? Word lines will be these row selectors and bit lines will be the column selectors, bit line and word line. So just look at one cell which has a word line and a bit line, and the word line is driving the gate of this transistor, this select transistor, okay, or access transistor, whatever you want to call it. Now, here is how we write into it. This is an NMOS, by the way, right? You apply VDD to the word line. That means the NMOS will be on. The NMOS is on NMOS being on means the capacitor will be connected to the bit line directly. Now, if you imagine the capacitor was previously charged to VDD. VDD represents 1. So it was storing logic 1, say. And then you drive your bit line to 0, to ground. Then the capacitor will discharge all of its voltage to the bit line, and then it will go to 0 voltage. That means you have successfully converted a 1 to a 0. That means you have written 0 into the memory cell. On the other hand, again, word line is on, right? VDD. That means the transistor is as if it's not even there. It's just a short circuit kind of thing. I'm like idealistically. Now, imagine the stored value was 0 to start with. It was discharged initially. Now you want to charge it up. You just apply VDD to the bit line. And then the capacitor will charge up from the bit line, and you have a 0 to VDD transition. That means 0 to 1 transition. So you can write into it. So does the write operation make sense? Isn't that very straightforward? Any question? Okay. Now, how do you read from it? That's interesting. Again, for reading or writing, you always need to activate your word line, right? That will connect this capacitor to the bit line, and then the bit line will do the trick. The bit line, let's see what the bit line does. Now for read operation, we keep the bit line at VDD over 2, half of VDD, and you will see why. Okay, half of VDD. Imagine, so this is the bit line voltage, VBL. This is at half of VDD. Okay, now let's consider that this capacitor was storing VDD already. That means it was storing one. Then it will notice that, hey, this node voltage is VDD, this node voltage is VDD over 2, and you have connected them by turning on this transistor. So they will try to balance the voltage, right? So this capacitor will start charging up the bit line now. It will do the exact opposite during the write operation, right? So the bit line voltage will start rising, increasing from VDD over 2. And the and what will happen to the capacitor? As it is charging up the bit line, it will lose its own charge, and its charge will keep reducing, right? At some point, wherever both of them will have the same voltage, then this process will stop. So if you look at the bit line voltage, which started from half of VDD, you will see it will gradually increase to some value and then stabilize, because that charging up has stopped. Okay. On the other hand, imagine that this capacitor was storing 0. Then the bit line will start charging it up, and as you see, the bit line will further discharge, right? The capacitor will gradually charge up and the bit line will further discharge. So you see something like this. The bit line started from half VDD, but this will further discharge, and whenever the two nodes have same voltage, then the discharge will stop. Are you guys with me so far on this? So we can create a difference in the bit line voltage, during the read operation, depending on, and the voltage will depend on what is being stored at the capacitor, right? Now, here comes the sense amplifier. A sense amplifier senses what is going on. There could be voltage sense amplifier or current sense amplifier. You can either sense changes in current or you can sense changes in voltage. Okay, so let's make it simple. Let's consider a voltage amplifier which has two inputs. One is reference and one is the input that you provide. Maybe the bit line voltage is our input and reference voltage. So typically we use a sense amplifier whose reference is at, say, half of VDD, exactly uh, what the bit line voltage initially was. Okay, so this is our reference, half of VDD. We provide a reference like this to the sense amplifier. Now, what this circuit does is, whenever you have the other input, it just compares with the reference. It compares the other input with the reference. If it is more than the reference, it creates a logic 1. If it is less than the reference, it creates a logic 0. Okay, so as you see, whenever the bitline voltage goes up, it becomes more than the reference, and the sense amplifier will provide, say, 0, and vice versa. So that's how you can select, you can actually sense what is being stored in the actual memory cells. Does that make sense to all of you or not? There is a problem, by the way, and I'll ask you about it. It's better if you guys ask me first. Anyone? Do you see any problem at all? No? Okay.
It seems that when the read operation is going on, isn't the CS losing its voltage?
Absolutely. Yes. Thank you for that. Yes. So the problem is the read operation is actually disturbing the stored data in the capacitor. While you're reading from it, you are disturbing the stored data. Imagine the scenario where maybe you are trying to watch a video. When you click on the video, you watch it, that's okay, but you also destroy what was stored. That will be very awkward, right? That's not useful at all. But that is the scenario for DRAM. These are known as destructive read operation, right? When you read, you actually disturb the stored data. What you need to do is, now that you have read, it was storing 1, you have to write back. That means after every read operation, you write back what you have just read to make sure you still have the same data for the next read. Does that make sense? This is not convenient, by the way. This is not a good thing, right? Because every time you read, you also have to write. It's not really beneficial when it comes to saving power, for example. But that's the only thing that you can do to make sure your data is still valid after you read once. Okay. So the read operation of these DRAMs will be destructive. That's the problem. Now, um, there are other things, other concerns here as well. But before I talk about the other concerns, can you confirm that you guys understand how we can read from a DRAM and how we can write into a DRAM? All right. I hope that's a yes. Okay. Now, by the way, before we talk about the problem, I want to just quickly show you the transient waveforms. I have already told you about this, and I try to draw it, but here is another dedicated slide to show you exactly that. So let's follow this. So this is the word line. Okay, so when the word line is 0, this is deactivated. This cell is deactivated, and nothing happens. By the way, right? Bit line is also 0, say, but the bit line, let's consider when the word line is on, say VDD, word line is on. Then before the word line is activated, we make sure the bit line is ready for action. Okay, so initially the bit line was VDD over 2. Now we have taken it to VDD. So we are trying to write into it. By the way, that's what you see here. First we will write one, then we will read, then we will write something else, then we will read, by the way. Okay, now let's see. Let's write one. To write one, I hope you remember, you have to add VDD to the bit line. Okay, and that's what you see here, VDD to the bit line. And then maybe the storage node voltage, which is S, that's what you see here. This was 0 before, and when you turn on the word line, it literally connects the bit line with the source, with the S terminal, and then it will gradually charge up to VDD. And I don't know if you have noticed, guys haven't asked me about that. NMOSes are not really good at passing VDD, right? I hope you remember that. But if you use PMOS, then you have problem with 0. If you use NMOS, you have problem with VDD. That's okay. We can live with it, by the way, because the sense amplifiers are sensitive enough to detect the changes. So we don't care. That's okay. So that's what you see. It doesn't really reach full VDD. It reaches VDD minus V threshold, as is supposed to happen for an NMOS. Okay. Now, so you have successfully written 1 because now this capacitor is charged up. Next, when you turn off the word line and bit line, see that node voltage remains where it was, and that's that means that your memory device is being able to hold on to the stored data. Next, now we will read 1, and here will be the challenge. And I told you that during read operation, the bit line is kept at VDD over 2. Okay, so let's keep, as you see, the bit line is kept at VDD over 2. VDD over 2. Oh, sorry, let me just show you that. This is VDD over 2, right? Bit line is kept at VDD over 2, and then you have turned on the word line here. And as soon as you turn on the word line, this is VDD over 2, and you had VDD here before. These two nodes will start sharing voltages, and then the bit line will start charging up. And as the capacitor is charging the bit line, it will lose its own charge and its own voltage will reduce gradually. And that's what you see here. See, the capacitor lost some charge and hence voltage, right? The bit line voltage increase and the decrease in the capacitor voltage will appear simultaneously. And then, by the way, we don't talk about what happens then, right? The sense amplifier already decides that, hey, so the bit line voltage increased above VDD over 2. That means it was storing 1, as I told you before, right? We haven't shown the sense amplifier scenario here. But by this time, the sense amplifier has already decided whether it was storing 0 or 1. So you have read from the memory cell, by the way. You know that already. Now, here comes an algorithmic perspective. If you already know that after reading this, we will be writing something, you already know we will be writing 0. You know that while you are reading, you have disturbed the stored data. That's okay because you're anyways going to write something after that. So then you don't care about writing back. But imagine your algorithm dictates that you just read and then you don't do anything. Maybe you will read again later. Okay. Then what you do? Then you read and then you write back. Okay. So in that scenario, it will be write 1, read 1, and then write whatever you have read. You have read, if you have read that it was storing 1, then you write 1 back. If you have sense that it was storing 0, then you write 0 back. Whatever it was storing, you write it back. That's the thing. If you don't plan to write something subsequently, but if you keep doing this, after reading you write anyways, then you don't have to, care about writing back, because anyways you are changing it. Does that make sense to you or not? Okay. And by the way, similarly, you can explore the write zero operation, where the bit line will be taken to 0, and you will see that the voltage at this node S will go to 0, because NMOS is a very good, NMOS can pass a very good 0, right? That's what you see. And then when you read 0, again the same scenario, again exactly same voltage sharing, charge sharing between the bit line and the capacitor. So you have destructive read. And I haven't told you about the other problem. The problem will be related to refresh. And what is that? Let me tell you. Imagine you are not reading, you are not writing, you are not doing anything to the memory cell. So the capacitor is supposed to hold on to the stored data. By the way, I'm always writing VDD here, but remember, practically you don't really reach VDD because of the problem with the NMOS. You reach VDD minus V threshold, right? Just keep that in mind. But for simplicity, I'll just keep writing VDD. So imagine you have VDD stored here, and you haven't been doing anything, reading or writing for a while. Will the capacitor be able to hold on to that exact same voltage level or not? Can anybody comment? When you're not reading or writing, the transistor is off. But even when the transistor is off, yeah, ideally it shouldn't have any current flow. But practically, there are leakage currents through the transistors, right? And because of the leakage current, the capacitor will keep leaking, charges. And gradually, if you don't read for a while, it will it will lose a significant amount of charge, and the voltage will degrade gradually. So it will lose the stored data. Okay, so the stored data will be corrupt. Now, what you have to do is, after a certain amount of time, you have to keep refreshing the stored data. And how do you refresh? You read and you write back whatever you read, right? You first read whether it was storing 1. If yes, then you write 1 back, and vice versa. Okay, so that's called refresh operation. Because of the dynamic, that's the reason why it's called dynamic, because this is all charge dynamics here. Charge dynamics need to be controlled. So after a certain amount of time, and by the way, if you're curious to know the time, it's not years or days or hours, it's microseconds, by the way. That's how fast the capacitors will lose charge. Okay. So within microseconds, maybe in 1 or 10, depends on the DRAM technology, in every 1 microsecond you need to refresh the stored data, which takes in a lot of power, by the way. That drains our batteries, which is not good, but we don't have any choice. This is the state of the art right now. And that's why we are exploring other memory technologies to solve this problem, which will not need this periodic refresh. Okay. But until then, we have to live with it. If you are wondering that, hey, if we keep refreshing that much, that means by the time we count 1, we might have refreshed maybe 1,000 times. That's true. The thing is, you have to know uh, how fast the modern day ICs operate. We operate in nanosecond region, not microsecond, right? We operate in nanoseconds time frame. So nano to micro is already 1,000 times. More like within 2 refresh, you might be able to do thousands of operations, say, in the best case scenario, right? So that's why it might sound like a very small amount of time or very fast refresh for you, but when it comes to the state of the art ICs, it's not really that much. Okay. So with the concepts of one terminal DRAM, now let's move on to the next variant, 3 terminal DRAM. And I hope you appreciate the problems with 1T DRAM, right? What is the good thing? Can anybody tell me one good thing about the 1T DRAM? Can anybody? Just compare this with, just look at this 3T DRAM. What is the first problem that you see here compared to 1T DRAM without even knowing how it works?
More transistors.
Yes, absolutely. More transistors means it will require a lot of area, which we don't like, because the more area you need, the less number of memory cells you will be able to pack into the chip. That means the storage capability will be low. You have to live with it, right? But 1 TB RAM is best because it has just one transistor. You can store a lot of data within a DRAM chip because you can fit in more and more memory cells. But the problems were refresh, and the other thing was destructive read. That was the main problem. uh, Destructive read is a serious issue, because every time you read, you write back, which takes in a lot of power and slows down the entire process. Now then, people proposed a different DRAM cell, 3 terminal DRAM, which solves this issue with destructive read. And here is how it does. Ignore this part for now. Just for now, just ignore these two transistors. Just imagine you have this M1 and this CS, these two components. And then it will exactly be like the 1 TB RAM. So we use different paths for reading and writing. So this M1 is writing, and there are two word lines now. WWL means write word line. RWL means read word line. Okay, so for writing, you use this transistor, and you write exactly. By the way, bit lines are also gonna be, there will be two bit lines as well: write bit line and read bit line, as you see. So let's just focus on the write bit line and write word line now. And if you focus on that, you will see you have the exact same DRAM cell. You write the exact same way. Nothing changed with the write operation. But now you don't read through the same approach. You radically change the read mechanism. You add two extra transistors, as you see. And this transistor is connected to the storage node. Okay. And during read operation, you turn on this word line. That means you turn on this transistor, and then you sense the bit line voltage from a different bit line, not the other one. You use a different bit line altogether, as you see. And here is what you sense. Imagine, say, imagine that you charge it to some value, say VDD over 2, say, or VDD, whatever. You charge it to some value. Okay. And this node was storing VDD before. It's storing VDD. If it is VDD, that means this NMOS is already on. Then there will be a discharge path from this bit line all the way to ground. So this RBL will discharge, right? On the other hand, if this node was 0, then this NMOS will be off, because NMOS 0 gate input will be off. Then there will not be any discharge path, or ideally. That means the bit line will not discharge. It will remain almost exactly at the level where it was. So you detect whether this read bit line is discharging or not. If it is discharging, then storing 1. If it is not discharging, then storing 0. Okay. To illustrate that, here comes a transient figure. I think this will be helpful. Let's look at write word line and read word line. Let's think about the write one operation. So for write one operation, you don't even care about read word line. Just forget about it. Don't worry about this at all. And you don't worry about the read bit line at all. Just think about the write bit line. And you can clearly see that when the word line turns on, the bit line is already set to VDD. You're writing VDD, that's why. Then the voltage at this node will rise to VDD minus V threshold, exactly like what happened to the 1 TD RAM. Okay. Next, when you read one, that means now you're reading, you don't care about the write branches at all. Write bit line, write word line, forget about them. Now you worry about the read word line. When the read word line is on, you look at the read bit line, by the way. Remember, we have just written one. So this guy, this node voltage is VDD. If this is VDD, this NMOS is on. That means you have a connection between these two. And then when you turn on the read word line, as you see here, you connect these two things. Read word line is connected to this transistor, right? So that's why you also connect this. So read bit line is connected to almost ground, as you see. So that's why the read bit line will start discharging. And by the way, while this read bit line is discharging, as you see, nothing is happening to the stored node, because the discharge is not happening through the stored node. It is happening through the transistors, the other transistors. So nothing is happening to the stored data. So you are not disturbing the stored data in any way. That's what you see here. That's the beauty of this design. Okay, and the read bit line discharged, and the sense amplifier will sense whether you had a discharge or not. If imagine if for some reason, you'll see next actually in the write zero operation. Here we have written zero, and you see written zero, and then when you read zero again, the read bit line doesn't discharge, right? As you see for the read zero operation, read bit line doesn't discharge. Why? Because if this was zero, this NMOS will be cut off, and then even when this transistor turns on, there will not be any discharge path at all to ground, so it will not discharge at all. So the good thing about this is you have non-destructive read. And by the way, it also solves to some extent the problem with refresh, because now, uh, I mean, the stored data is kind of safe because you have an additional gate capacitance as well. See, this transistor gate capacitance is there. So you have added capacitors. So technically, the discharge rate in this type of DRAM is not as much. So oftentimes we can get away without having any refresh operation, without needing any refresh operation, right? Uh, that's okay. And don't worry about this incomplete swing SS. I hope you know what swing means, right? 0 to VDD transition is the complete swing. And as you see, at node S, you don't have complete swing. You have 0 to VDD minus V threshold. That is the problem with the NMOS, right? And there is just one suggestion how you can solve it. There is one thing, word line overdrive. That means you increase the word line voltage beyond VDD, like VDD plus delta V, to increase this voltage. This is a possibility, but don't worry too much about it. This is a technique that we haven't discussed in this course. These are some special techniques. So anyways, don't worry too much about this, but I just wanted to explain quickly. Okay, so this problem can be solved. This is not a bottleneck in any way. We don't care about it. Okay, now, so DRAM, there goes DRAM. Now we're ready to talk about 6 transistor SRAM cell now, which has a radically different operating mechanism compared to DRAM. And as you can see, you have more transistors, so more interplay. There will be more things to talk about. But let me stop here for a minute and for a second and see whether you guys are, getting what I'm trying to explain. Do you guys have any questions? No? Okay. So a 6 transistor SRAM cell looks like this. Don't look at the circuit first. Look at this simplified circuit first. This one. The reason is it is actually very simple. You have cross-coupled inverter. And can anybody tell me where else we have seen a cross-coupled inverter in this course? These guys, cross-coupled inverters. Where else? Anybody remember latches and flip-flops, right? Remember in the latches and flip-flops, we used to always use these cross-coupled inverters because these are the fundamental storage component. Okay, so what these inverters do, and we have talked about it many times, that say if you have 0 input in one of these inverter, the output will be 1, and this 1 input to the second inverter will create a 0 output, and meaning they will keep each other states intact. As long as the inverters are active, these two nodes will hold on to the stored data. It will not easily change. Okay, that is the reason why these cross-coupled inverters are always used as fundamental storage elements in latches and SRAMs as well. So SRAM uses a cross-coupled inverter like this. And then you use 2 extra transistors. So by the way, how many transistors are there in the cross-coupled inverter? 2 in this inverter, 2 in this inverter. So 4 already gone. You just need 2 more transistors. And here comes one. It allows you to access this node voltage, and the other transistor allows you to access this node voltage. And the node voltages are treated as like Q and Q bar. That means if this is 0, this will be 1. If this is 1, this will be 0. Exactly opposite to each other. Okay? Because of the cross-coupled nature of it. And the access transistor is there to allow you to read what is stored here in this node or write into the storage node to selectively change the storage node. Okay. Now, how do we write? How do you write into it? Imagine if this is 0, this is 1. Just imagine that. you just look at it from maybe one perspective. So if you see this is 0, by the way, let's just talk about the q instead of q bar. Okay, let's consider this. If you see that q is 1, you say that, hey, the SRAM is storing 1, even though there is 0 in the other end. That's okay. You just read, you just sense 1. So q is storing 1, that means the SRAM cell is storing 1. If you want to change the stored data, you change this 1 to 0, which will also change this 0 to 1 at the same time. That's okay. But you still say that, hey, we have written 0 in the SRAM cell from 1 to 0. Okay, you just look at the store state of the queue. You can also do it q bar. That's okay. It's all the same. Doesn't matter. Now, by the way, if you expand the structure, you end up with this type of scenario. You have this one inverter, and this is another inverter. They are cross coupled because the output of this guy is the input of the other one. The output of this guy is the input of the other one. Okay, now it looks a little bit more complicated, but I really like looking at this figure because it simplifies everything, right? So just keep that in mind. You can draw, just first draw two inverters like this. Oftentimes we have to do this to discuss the details of operation, because you actually have to expand the transistors to see the details of read and write operation. We will do that in a few minutes. So the output of this guy, let me just do this with a different color. The output of this is the input, by the way, sorry. The input of this guy, this inverter, will be connected to the output of the other inverter. See, let's see if that makes sense, right? Input of one inverter is connected to the output of the other one. And next, the input of the other inverter will be connected to the output of this inverter. So I hope that makes sense. Okay. And then, by the way, where do you connect the access transistors? Here is one connected directly to the storage node. By the way, the output nodes of the inverters are the storage nodes. So if this is Q, the other output will be Q bar, and vice versa. And then you connect another access transistors directly to the storage nodes, Q and Q bar. And notice something else. Both of these transistors, both of these access transistors will be connected to the same word line. So they will be activated together. You cannot selectively activate just one or the other. You need to activate both of them together. Just keep that in mind. And there are two bit lines. One is bit line, just bit line, and the other one is bit line bar. Even though they might have same voltages in certain scenarios, I'll tell you that, but they're still called bit line and bit line bar. Okay, two bit lines. Now, with that idea in mind, let's move on and see how the SRAM read-write operation is performed. Let's first talk about the read operation. Okay, are you guys with me so far? Ready?
Yes.
Okay, thank you. Let's go ahead with the read operation first. For read, you first pre-charge the bit lines. Pre-charge means you just charge them to a certain level, and then you don't drive them using a voltage source anymore. You just let it go. Just pre-charge and let it go. And then if it wants to discharge, fine. If it wants to charge up further, fine. You let it do its thing, but you don't drive it anymore, right? You drive it up to a certain level, charge it up, and then you let it go. You don't drive it with a voltage source. Just keep that in mind. Pre-charging to a voltage and applying a voltage is not the same thing. For write operation, we apply VDD. For read operation, we pre-charge to VDD. Just keep that in mind. For write operation, we keep driving with a voltage source to VDD. For read, we just pre-charge and let it go. Let it do its own thing. And here is what it does. Let's see. Both of these bit lines will be VDD to start with in the read operation. Even though they are named bit line and bit line bar, they're not always the opposite, like I said. Okay, let's consider just put those things here as well. Bit line and bit line bar both at VDD, and that's what you see here. And just to illustrate how the bit line will be able to hold on to VDD, here comes the answer. Bit lines will have capacitances, right? Bit line capacitances, so word line capacitances, they will always be there. The bit line capacitance will hold on to the hold on to the voltage for a while at least. Okay, now imagine that you are storing 0 here and 1 on the other hand. Okay, just without any loss of generality, you can do the exact opposite, doesn't matter. Let's consider this is 0 and this is 1. Can you guys help me understand which of the transistors will be on and which of these transistors will be off, right? Let's try to find out together. So this 0 is connected to this inverter, and it will be fed to this NMOS. So this NMOS will be off because NMOS turns off with 0 input. Okay. And by the way, one more thing, this node was 1 and this node was connected to this input. And this was fed to this PMOS. So this PMOS has an input of 1. PMOS with a 1 input will be turned off. So this PMOS and this NMOS will be turned off, right? So if you draw the circuit without this deactivated NMOS and PMOS, then you have something like this. So this PMOS is missing and this NMOS is missing. Okay, these two are missing. I hope that makes sense. Do you see that? Okay. Now that simplifies the circuit, right? Let's just look at what we have at hand right now. Imagine you have not imagine, you had VDD before, and this PMOS is connected to VDD as well. As you see, the PMOSs are always connected to VDD and MOSs are connected to ground. So this node is also VDD. This node is VDD. This PMOS is on. Okay, because why this PMOS is on? Because the input to this PMOS gate is 0, as you see. Okay, so this PMOS is on, but you have VDD in both ends, here and here, both VDD. So there is no voltage difference. There will not be any current flow or anything, no sharing or discharge or anything. So the bit line in this end will remain where it was before. Nothing will happen to it. On the other hand, let's consider this bit line, which also was at VDD, but now this storage node was 0, and this is also ground 0. And when you turn on the word line, this transistor connects the bit line with the storage node Q bar. Do you guys see that? And this NMOS is also on. Let me just simplify this a little bit. So this word line is VDD, word line is on, so this transistor is on, and this transistor is also on. So do you see that this VDD and ground will be kind of connected, right? And then this bit line will start discharging through these NMOSs, right? So then the voltage at this bit line will start reducing. So just one of the bit lines will start decreasing in voltage. Do you guys agree with it? Do you have any questions? But how far will it discharge? That's the question, right? Just imagine. Yes, it will discharge. By the way, before talking about how much it will discharge, let me tell you what we do next. So both of these bit lines started with VDD and VDD. One of them started discharging. What you do is, remember the sense amplifier, the voltage sense amplifier, it uses a reference and another input voltage, right? So the good thing about SRAM, remember there was a term called differential sensing or differential read. What it means is you don't need an external reference. You don't have to create an external reference. It will serve as a reference to itself, because say this is bit line and this is bit line bar. You just provide bit line and bit line bar together. As you see, one of them were staying constant, right? So if bit line bar reduces, imagine if bit line bar reduces, then this node was storing 0. If bit line reduces, then the other node was storing 0, right? You can sense, you can compare these two, which one is larger. This is larger than that, or that is larger. A or B, right? Is A is greater than B, or is B greater than A? You can easily sense using this sense amplifier, and you can sense whether it was storing 0 or 1. Okay, so this differential sensing is more like self-referenced. You don't have to create a different reference circuit. You might wonder, hey, why do we mind having a separate reference? Actually, you can create separate reference if you want to, right? And that's possible, that is done. But the problem is reference generation circuitry is a pain. Yeah, we haven't talked about it, we will not talk about it, but typically to create a stable reference is a major problem, is a major concern in memory array design. That's why whenever you have a memory, that is differential, that means that is self-referenced, that is a huge benefit for us in every respect. Now, coming back to the case where, okay, this bit line will discharge from VDD to something, but how far will it discharge? And while it is discharging, remember, we are not trying to write, we are trying to read. We just want to sense and let it go. We don't want to change the stored data at all. But while this is discharging, by the way, this node was zero. If bitline discharges, this will gradually charge up the storage node, and it can change this zero to VDD or something. And then you have a disrupted read operation, right? Disruptive read, destructive read, which is a problem. You don't want that. What saves you is that, imagine, although I'm telling you that this transistor is on, so short circuit, this transistor is on, so short circuit, that's not true. Where even when the transistors are on, they still have finite resistances, right? This M5 will have a resistance, RM5 say, and this M1 will have a resistance, RM1. And then you have this storage node voltage, which was initially zero, right? So I can read, and this is VDD. So I can read all this circuit like RM5, RM1, and then ground. And this is the storage node that you care about. And this is VDD. And this voltage, maybe VQ, will be RM1 by RM1 plus RM5 times VDD, whatever you apply. And you want to keep it to zero. You want to keep it to zero, but it will not be zero, obviously, as you can see clearly, right? It will increase to some extent, but you don't want it to increase too much. You just want it to increase slightly, and then let it go. Then it should come back to zero. Okay. So can anybody tell me, please answer, please try to answer, how can I ensure that this node voltage doesn't increase too much beyond zero? It increases slightly, but not too much beyond zero. How can I ensure that? Any idea?
We can make it smaller with respect to RM5.
Yeah. So in terms of resistances, yes, thank you for that. In terms of resistances, you can increase the resistance of RM5. That means, as you see, if RM5 increases, the voltage at this point, VQ, will reduce, right? The voltage in a voltage division scenario, the larger resistance will take the greater share of the voltage. So you make sure the RM1 has a smaller resistance. And how do you make the resistance of a transistor smaller? By sizing it up compared to the other one. You increase the size of this transistor. Okay. So that means there are design challenges, design requirements necessary, right? Now, let me ask you something. Let me, all of you, I mean, please, you guys should try to answer, even if it is wrong, that's perfectly fine. And I will appreciate if all of you try to participate, right? Uh, Now, my question is, so this voltage was supposed to be zero, but we increase it to some value, say, for example, 0.2 volt. Wouldn't that already change the stored data? Wouldn't that already corrupt the stored data? Let's see whether somebody can add a comment to it. How will, I mean, after we are done with the read operation, will this node go back to zero, or will it stay at 0.2 volt? That's what I'm asking. Anyone?
It should go back down to zero.
Why? First of all,
Because
thanks for responding. And yeah, please go ahead.
because M5 should turn off, but M1 should still be on.
Yes, this is an interesting approach, but I think the easier approach would be to just go back to this figure. Imagine this node is which one? This node was supposed to be zero, right? This node is this one. Remember. Now, do you see what's going to happen? Say this guy going from zero to, imagine our VDD is 1 volt. VDD is 1 volt. Okay. If this guy is 0 or 0.1, will it make any difference to this inverter?
No.
No. as long as, even if it is 0.2, 0.3, it shouldn't, as long as it doesn't exceed 0.5, right? Remember that VM, right? Logic threshold voltage. This, all of this should be treated like a zero by this inverter. So this inverter will create a VDD as at its output, and that VDD will create, again, try to create a zero, because this inverter will see, hey, my input is VDD, I should create a zero. It will not be able to put it to zero because you are driving it using the bit line, which is stronger, by the way. Bit line is stronger, a strong driver. Okay. But when you're done with the read operation, when you disconnect the word line, that means your access transistors are disconnected, then even though this voltage was 0.2 for a while, this this will treat it like a zero. This will be VDD, and then the output will again be zero, and it will drive it to zero again. So it will recover whatever you have changed, it will recover, right? Does that make sense? So this inverter is saving you. Remember, towards the very beginning of this course, I told you that VTC, voltage transfer characteristics, is a very important thing. V out over V in. What is saving you is this, the fact that the VTC remains flat for a while. If you apply 0, you have VDD. If you apply 0.1, you still have VDD, and so on. As long as you don't exceed the logic threshold voltage VM, you are safe. Okay. So that is the principle that we are using in the SRAM design as well. Okay. Now, if I ask you, can you let this node voltage to arbitrarily rise? For example, it was storing 0 before, and now it is sharing charge with the bit line, and it is the voltage at this node is increasing to some extent. Can I allow it to increase it to some random value? How far can I allow it to increase? Anyone?
At least below half of VDD.
Yes, thank you. Because exactly the same problem, right? If it exceeds half of VDD, then the inverter will recognize it like a high voltage, high input. That means now you have actually disrupted the stored data. So you have to make sure, and can anybody tell me a way that might result in such a scenario, just involving this RM, so M5 and M1, just involving this M5 and M1? Can anybody tell me a way to create this problem? I want to intentionally create this problem, right? How can I do it?
Give M5 a low resistance value.
Thank you so much. Yes. Yeah. Just increase the size of M1. It's maybe for some reason, hey, I like all of these transistors to be larger. Let's make our M5 also large, right? For some reason, you make the M5 large enough, and then M1 will take a greater share of voltage, and suddenly it might actually go over VDD over 2. So there is a delicate balance. I'm giving you a hint here. At some point, you'll see in this lecture that we will actually have to size up this M5 for some reason. For some reason, we'll have to size up this M5. But we have to keep in mind that, hey, sizing up this M5 too much will lead to greater voltage appearing across M1 that you see here. And that might lead to this accidental data flip. So these are called design trade-offs. That means you try to improve something else get damaged, right? You have to make a balance to make sure everything is optimized, not just one. Okay. So these are design challenges that we live with every when it comes to SRAM design. But I hope at least the read operation for SRAM makes sense to all of you, right? This is the read operation of SRAM that we have just discussed, and read operation is differential in nature. Now let me go back to this figure again. This is the exact same figure, but resized. We will talk about a different concept. I hope by this time you appreciate the ratio between the resistances of M5 and M1 is important, right? M5 and M1 is important because that's what is dictating how much voltage will appear here. And that's what will dictate whether you will have a reliable read operation or whether you'll have a destructive read operation, right? Which we don't want. Now, there is a performance parameter that we use to represent that. This is called CR, or cell ratio. Let me write it here, cell ratio. And the ratio is nothing but the ratio between the sizes of M1 and M5. That's what you see here, W1 L1 by W5 L5. And I hope you already know, we don't really change the L, gate length. We try to keep it the same for technology, 14 nanometer technology, 32 nanometer technology. blah, blah, blah. We just keep them same. So essentially you have control over the width. Okay. So you can also treat it like W1 over W5. And this is what you see here, voltage rise of node storing 0 volt. That this voltage, how much will it rise? Will it go to 0 0.1, 0 0.2, 0 0.7, right? That's exactly what you see here. Now, can anybody tell me which portion is good? Going here is good or going here is good? Is the green direction good or the red direction good? Please try to answer. Someone.
Greater, the green direction.
Yes, because if the exactly because of the same reason, if you keep going to this direction, that means the voltage will keep rising and you'll have a failure, right? You don't want that to happen. Now, as you see, cell ratio, by controlling the cell ratio, you can, tune it. That's the good thing. Now, it also shows you that the larger the cell ratio, the better the performance is, right? The concern with voltage rise at that node will be not as much. Okay. So cell ratio is what? The ratio between W1 and W5. To increase CR, we will have to increase the numerator, right? That means W1 will have to be sized up. And that's what you see here. This W1 means M1 will have to be sized up. Or in other words, you can reduce W5. That means W5 will have to be sized down. Remember, just keep that in mind. There has been a scenario where sizing down M5 is important. Sizing down, not sizing up. Just keep that in mind. Okay. So are you guys all with me so far?
Yeah.
Okay, sure. So let's move on to the next one. And by the way, if you guys try to answer, I mean, even if it is wrong, that's perfectly fine. Like I said, it will really help you understand these scenarios. Now, next, write operation. Here is how we write into an SRAM cell. Okay. I hope you recognize this diagram right now. This is just the simplified version because of storing 0 and 1, right? We are storing the same thing, 0 and 1 to start with, and some transistors are disabled. So we kind of remove them from the picture to make it simpler. Now, for write operation, you apply the opposite voltage, with respect to the storage node. For example, here you have 0 in the storage node. So you want to flip it, right? And we flip both, by the way. When one of them flips, the other one also flips. So if you have 0 here, the corresponding bit line will be set to VDD. And if you have 1 here, corresponding bit line will be 0. Now you actually have bit line and bit line bar, by the way, right? By the way, you also see that here, bit line and bit line bar, opposite. So it was previously storing 1, you want to change that. That means you drive your corresponding bit line or bit line bar to 0. Okay? Simple concept. What you do is you turn on the word line. This guy, this access transistor turns on. And now, remember I told you, driving and pre-charging are different. For read operation, we just pre-charged and we let it discharge. Imagine if it were the case that we are driving with VDD, imagine not pre-charging, just driving with VDD, then this node will definitely be disturbed because you have such a huge drive, strong drive from the bit line that you will not be able to balance it in any way. Okay. But for write operation, you want to change it. You want to disturb it. That's why you drive it with a driver, write driver. So then this node will have a VDD, right? It already has a VDD and you are driving it to ground. So this will discharge to ground. Easy. And this guy was at 0, you are driving with VDD, blah, 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 right? I hope you see that. There will be scenarios where you'll be able to kind of discharge or charge at will because you're driving with bit lines now. Does that make sense to all of you? Write operation is simple compared to the read operation. You just put the voltage that you want to write into the storage cell. You want to write VDD to the storage cell, add VDD to bit line and drive it. Done. Let's see, we define another metric called pull-up ratio. Why pull-up? Because it is related to the pull-up transistor, right? That's why pull-up ratio. And that's what you see here. By the way, we needed the M6 to be larger. Remember that M6. So M6, the size of M6 is in the denominator, right? The size of M6 is in the denominator. So if M6 is larger, the pull-up ratio will be less. The lower the pull-up ratio, the better it is. Uh, and remember, and this is a plot which shows the voltage fall of node storing one. Voltage fall meaning this node was at VDD. You need to reduce this voltage as much as possible, right? Say from VDD all the way to zero. That would be ideal. But this plot shows uh, the level to which you can bring down this voltage. Say from, if your VDD was 1 volt, here you have brought down to 0.4 volt. You actually want to go ideally to zero, by the way, right? 0.4 volt. So the lower that you can bring in this voltage, the better it is, because the inverters will be able to flip easily. So you prefer going to the left, remember. And as you go left, your pull-up ratio reduces, as you see. And how to reduce the pull-up ratio? By sizing up the uh, M6 transistor. And as I told you before, it is easier to see just based on this understanding that M4 and M6 will fight with each other. We want M6 to win when we are trying to write, right? So just make it larger. That's it. It's easier to see. But also keep in mind the expression for pull-up ratio, because these are standard expressions used in industry. If you ever join a chip making company, uh, and work on SRAM design, they will always talk about pull-up ratio and cell ratio, right? So you need to be aware of what it means. Now, here are some metrics, that some design metrics which determines which are widely used to determine the performance of SRAM circuits. Hold stability. It shows whenever you are not trying to read or write into read from a SRAM cell or write into an SRAM cell, the SRAM itself should be able to hold on to the stored data. For example, the word line is off, so we have zero word line. We are not trying to read or write. So whatever was being stored, 0 and VDD, should remain so. Because if I decide to read maybe 10 minutes later or half an hour later, I should still be able to read 0 and VDD without any problem, right? So this stored data should remain so. And how is it being stored there? These inverters are driving each other relentlessly, and they're keeping this voltage intact. And that's called hold operation, because they are holding on to the data. Okay. Uh, all right. Now, by the way, let me ask you a very simple question. And oftentimes, surprisingly, people make a mistake there. Oh, let me just write it here. Stronger. Okay, right. Erase that, unfortunately. But anyways, now here, let me ask you something. So this word line is off. These two transistors are off. I'm not trying to access it. These two nodes are storing data. Let me ask you something. As this circuit is storing data, will there be any external power required, or will it be able to store it indefinitely without spending any power? Can anybody tell me? That means, can I turn off the supply voltage? Is there any supply voltage here? Am I supplying any voltage at all in the circuit when the word line is off? Am I supplying any power to the circuit at all? Can anybody tell me?
The VDD attached to M4, is it supplying the power?
Yes, thank you. So if you look at this simplistic circuit, people often forget that inverters themselves will need VDD. Let's go back to this circuit, right? So essentially, this part is active. And within this part, you have VDD, as you see. So you have to constantly keep providing VDD supply to make sure these inverters work. The only reason why these nodes are storing the voltage or driving each other is because the inverters are active. And to make sure they're active, we have to keep providing VDD. So that's the fundamental difference between SRAM circuit, SRAM memory, and the other memories that we'll talk about later in the lecture. SRAMs are called volatile memory. That means they will lose all their data if the supply is gone. Okay, they will not be able to hold on to the stored data. As just compare that with a portable hard drive or a flash drive. Okay, you can take it out of the USB port and it will still hold on to the stored data. Next time you plug it in, you'll see that stored data that was there, right? So these are made of non-volatile memory, and we will talk about them. The memories which can still hold on to the stored data even when the power is taken out. Okay, so with that idea in mind, I hope you understand what hold stability means, right? How well the SRAM cell can hold on to the stored data even when it is not being accessed. Read stability. I hope you understood that during read operation, there is a chance that we might accidentally program the cell, or change the content of the cell. That's not good. That's bad, right? We have to make sure our cell is stable enough to not get disturbed during read operation. That's dictated by the read stability metric. Writability. When you are trying to write, you notice that there is a chance that there will be a fight between two transistors, namely M4 and M6 in this slide, right? And there is a chance that simply because of the fight, we might not be able to write into the SRAM cell. And that shouldn't happen. So the writability matrix uh, judges how easy it is to write into the SRAM cell. Access time and read time, I mean, these are straightforward. How much time it takes for us to write or read, right? Cell leakage, while you are operating, the transistors are leaking even when they are not supposed to. That drains power. That's a metric that is related to the power. Cell area, that dictates the layout area of the overall SRAM cell. The smaller you can make the area, the more SRAM cells we will be able to fit in within the same chip. So the lower the area is, the better it is. We always try to make sure the things are compact. And read-write power is a concept that is true for any memory or any circuit that you talk about, right? If you can reduce the read power or write power, always better. Your batteries will hold on for longer. Now, with those ideas in mind, let's try to see how transistor sizing can affect these metrics, and how there are design conflicts and conflicting requirements in this SRAM cell design. Let's take one thing at a time. Better read stability. You notice the read stability was related to the relative sizes of M1 and M5. We don't want to let this node voltage rise too much, right? Remember that. And that was related to the pull-up ratio. And I just kept this note for you guys. We decided that M1 should be stronger or larger, and M5 should be smaller or weaker. If just focus on M5. Let me put a marker here. M5 is an excess transistor. Remember, it's not about M5 or M6, right? Both of them are excess transistor. This node will not always be zero. It might be VDD. Then the other node will be zero, right? So we have to, this is a symmetric circuit. So whatever applies to M5 will also apply to M6, as you see, right? So let's keep that in mind. I'm talking about the excess transistor, and it should be smaller or weaker. Just keep that notion in mind. So, see, why is it letting me? Okay. Give me a second. Sorry. Yep. Okay. Now, for better read stability, we have just talked about that the excess transistor width should be reduced and the pull down transistor width should be increased. We already know that. For better writability, we also talked about the oh, anyways, so we talked about the cell ratio. By the way, for read stability, we talked about the cell ratio. For the writability, we talked about the pull-up ratio. And we just finished talking about the pull-up ratio, where we mentioned M6 should be larger. Okay, let me write it here. That will be easier. M4 should be smaller or weaker, right? So M6 needs to be larger. Just notice the term. For the other one, between M1 and M6, my tab is acting weird. Sorry. Anyways, so let me write it again. So M4 should be larger, and M4 should be smaller. On the other hand, between M1 and M5, M1 was supposed to be what? Smaller or larger? Anyone? Let me take a quick test. Just look at the cell ratio. The larger the cell ratio, the better it is, right? To make it larger, W1 should be
Larger.
larger. So This should be larger and this should be smaller. Now, take a moment to see this conflict. Because based on the better writability concept, we need this excess transistor. I told you it's not about M5 or M6, it's about the excess transistor, both, right? We need this M6 to be larger, but for better read stability, we need this M6 or M5, whatever, to be smaller. So what should you do? Should we make it more writable, or should we make the write easier, or should we make it more stable? That means make the read stable, right? So that shows you a conflict right away, that hey, we have conflicting design requirements and you have to optimize. You have to, do some trade-off so that it is not, I mean, if you optimize the read operation to the fullest, the write will be really bad. The write will suffer. Or on the other hand, if you make the write operation perfect, the read operation will suffer. So you cannot make the best of both. That's the problem with this 6 SRAM transistor. You have design conflict. Let me know if you guys got the concept of conflict, right? Rather than just look, oh, there are design conflicts. Rather than just talking about having design conflicts, we are looking at the conflict right now. That hey, the same circuit asks us to do something for one operation and do something else for the other operation. We cannot do both. We will just make one transistor circuit, we will fabricate it, and then we are done. We cannot dynamically change the sizes during read and write. We have the same transistors during read and write. So you have to make sure you find a balance which does good to both. Okay. And by the way, we can go through the rest of the release. For example, to lower the or reduce the access time, you need faster access. So you size up these two transistors. You can read them. I'll just like quickly go through. Better hold stability. To make sure hold stability, that means when you are not reading or writing, the cells can still hold on to the data. You need to balance out the PMOS and NMOS transistors. So you need their sizes to be almost balanced, like such that they are balanced. Okay. And to lower the cell leakage, you want all of these transistors to be minimum size. That means smaller. See, sometimes we needed larger transistor, but that will create problem with the leakage. And of course, cell area. For cell area, you need minimum size transistor. So what do? There are so many conflicting requirements. For one thing, you need smaller transistor. For other things, you need larger transistor. For right, you see there are so many conflicts that are present in the SRAM cell design, and that's what makes it so challenging and interesting to design these circuits. And people live with all of this. They find a fine balance to make sure the overall performance is satisfactory. So with that, there are another way around this problem. So far we have just talked about 6T transistor cell, which is the mainstream version. There are other proposed variants, and they're often used in certain applications. 5T, which uses 5 transistor, so it gets rid of one of the excess transistor, just makes it one. It saves one transistor, lower area, but it has other problems. Remember, there is one term that I should tell you, focus on: single-ended and differential. When you have bitline and bitline bar, you can compare between these two, and you can easily sense when you have two lines which you can look at and compare against each other. That is a differential kind of sensing, and that is always a better way. Differential sensing is easier and better and more reliable. But when you have just one line, whom do you compare against? You create a separate reference, and then you compare these two against each other. So creating this reference is a challenge, and it's not really as reliable as having already existing references like bitline and bitline bar. So we don't like 5T too much. These are not only 5T, 5T, 8T, 10T. By the way, the T means how many number of transistors, right? 8T has 8 transistors, 10T has 10 transistors. They are good for some reasons. For example, 8T and 10T, as you see, these have decoupled read and write operation. You have just noticed that there are conflicting requirements for read and write. If you want to make read better, you do something. If you want to make write better, you do the opposite. Uh, but how about we decouple the read operation and write operation completely? Again, we will not go into the detail of these 8T and 10T operations, but I just want to tell you that uh, these designs separate out the read operations. So only write happens within the 6T, and the other two transistors are used to read. And for the 10T, as you see, there are 6 transistors for write and four other transistors for read. So there are reasons for both of these. There are applications where they can be utilized, but in general 60 is the best choice, best mix of size, because 10T and 80 will definitely be larger in size, right? But if you absolutely cannot live with 60 for some very specific application, you might want to go for 10T or 80, right? That's the thing. But remember, uh, these transistors 5, 10, and 8, they are single-ended. The rest of them are differential. So differential is something that we really like. For example, even 70 is differential. So they have a one additional tiny transistor snuck in between the cross coupled inverter. That's what makes it 70. Anyways, if you're interested, there are some links of some papers from where, remember, all of these that they are learning were research problems at some point. Somebody came up with these ideas and now these are mainstream. Okay. Uh, Anyways, let's move to the next one. Parameter variation. So when we talk about different circuits, we assume as if things are ideal. So we will get the exact same circuit that we meant to design. We wanted this much size, we wanted this much threshold voltage, we wanted this much on current and off current. But if you make 10 samples of the same circuit, they will all be different from each other, because we cannot control everything to the fullest extent. There are certain degree of control, but there will always be some variation, some distribution of the overall parameter. And this is a fundamental part of our chip design, and we have to be aware of it. So there are two components. Remember, so uh, you have multiple wafers. So one wafer, wafer one, wafer two, wafer three, and so on, right? You are making the same circuit in all of these wafers, all SRAMs. Maybe in wafer one and wafer two, usually there are variations between different wafers. So these are called, or die, by the way, die. They're called inter die, like between different dies, different die variation. So you have let me tell you something. Say you have taken in one wafer and you bring in one die, and you have taken another die. This is inter die variation. Inter die, as the figures show you, right? Within a wafer you have different die. We talked about dies and wafers before. Each of these rectangular components will be one die. So between two dies, within one die you have multiple SRAMs, by the way. As you see, each one of these dies will contain multiple SRAMs and transistors and whatnot. And between them there will be some additional sources of variation, right? That's called intra die. So inter die and intra die. Okay, so there are two levels of variation, and by variation we mean, say you meant to design a parameter to be some exact value, but you will actually get a distribution of that value, more like you'll get some more and some less, as essentially like a Gaussian distribution. And that's what we talk about. That's what you see here, a Gaussian distribution. And the distribution that we're looking at is usually for threshold voltage. Some transistors will have higher threshold voltage, some transistors will have lower threshold voltage. And that's what we actually often talk about. And the inter-die variation is called the global variation. It's more like, in large scale. And intra-die variation is often called local variation, right? In a small scale. So that overall variation will be combination of global variation plus local variation. Easy to see, I hope. And by the way, let me tell you something. If this is a threshold voltage, right? We are looking at the distribution of a threshold voltage. If you are in this side, you'll have larger threshold voltage. Remember, larger threshold voltage make a transistor weaker. We talked about this way before, towards the beginning of this lecture. Not this lecture, the beginning of this course, where we talked about MOSFETs and FinFETs, right? And their threshold voltages. So larger threshold voltage makes a transistor weaker. And you notice that having a weak or a strong transistor makes a lot of difference in SRAM operation. If for some reason one transistor is supposed to be stronger, but because of having higher threshold voltage with variation, it ended up being weaker, then you can have catastrophic failure in the SRAM operation. So we have to be mindful and careful about the existence of this variation. And here are some examples. Imagine this is your threshold voltage distribution. This is supposed to be the nominal, the ideal value of threshold voltage. VTH, but you can end up with values in both direction, more threshold voltage or lower threshold voltage, right? So higher threshold voltage will make your transistors weaker, and wherever you need stronger transistors, you will suffer. For example, excess will be problematic because for excess you needed stronger excess transistor. So excess operation can fail, and that's why you might have greater chances of excess failure. Write operation might fail because during write operation you need stronger transistor. The excess transistor should be stronger. For some reason, if the excess transistors have higher threshold voltage, they will be weaker, and you can have write failure. So these are problems with higher VT than usual. And this zone is called high VT corner. Okay. And how about the low VT scenario? If the transistors have lower threshold voltage, then they will be stronger, right? I mean, they will have more current. But for in certain scenarios, you don't want them to be strong, too strong. For example, during read operation, if certain transistors are too strong, for example, if the excess transistor is too strong, then they will end up writing into the cell during read operation. So you'll have read failure. And same thing applies for hold operation. So low VT corner can lead to greater read failure and hold failure, and high VT corner can have other failure. So you have problems in both direction. It's not like we can have this or that. We always try to stay within, the ideal as much as possible. And our design should account for some margin of error, because you will not get exactly that value. You will get some more and some less. We have to take into account while designing the SRAM cell, this presence of variation. Now, that concludes the discussion on SRAM, and we will move on to the next level of discussion on non-volatile memory. I've just told you SRAM is a volatile memory, and there are by the way, let's look at a category of memory: volatile and non-volatile. Under volatile, there are so many different memories like SRAMs and DRAMs. We talked about both of them. They need power supply. I mean, if you remove power supply for DRAM, if you remove it for a few microseconds, they will lose the stored data. For SRAM, even sooner, they will lose the stored data even sooner. Anyways, there are other forms of DRAMs which we didn't really, we talked about just two, like 1T and 3T DRAM. Anyways, there are different variants of DRAMs as well. Now, and rest of them are all non-volatile, as you see. There are very few volatile memory variants, but there are a lot of non-volatile memory variants, because we need non-volatile memory quite a lot, because we cannot just keep providing power indefinitely to the memory storages, right? We want to store them somewhere. That's why there are so many non-volatile versions of memories. And there are some prototypical memories which are currently being explored: phase change memory, magnetic RAM, STTM RAM. By the way, as you see, we will talk about that. It's not really only prototypical anymore. It is moving towards application right now. Okay, there are certain companies like Everspin that are selling STTM RAMs to mass population. But there are other memories like emerging memories, like carbon-based memory, MOT memory, which you will not heard about, which you will not hear about too much, because they are currently in the R&D phase, research and development phase. The good thing about, as you see, this green zone memory is because they fall under the category of 4F square footprint. You may not know what that is. This is more like an indication as to how compact these memories are. 4F square, the minimum that we can get nowadays. Okay, so the closer a memory is to 4F square, the better it is in terms of integration density. Okay, so all of these memories are already 4F square compatible. Not these ones, by the way. These will take up more area. So the non-volatile memories are good for two reasons. They will take up less area, and second is they will be able to hold on to the stored data without having external power always added to them. Okay, now here are some perspective as to why we still like SRAM so much. If you compare the write time or program time, you see how fast the SRAMs are. There is nothing that even compares with the speed of SRAM, by the way, as you see, right? SRAM is the fastest. This is the time axis, so the lower the better. And by the way, endurance, that means how many times you can you read and write from them. You can literally read and write from them from 10 raised to 18 cycles. Just imagine how many that is, right? 10 raised to 9 is a billion times. Just imagine. So a billion, right? So you can read and write from SRAMs. You can keep doing it almost indefinitely. That's why they have super high endurance, and they are very fast. But when it comes to say dynamic RAM, it's almost close in terms of it's same in terms of endurance, and almost close in terms of write cycle. But DRAMs have other problems, as you know, right? Destructive read and whatnot. And there are other memories like flash memories, resistive RAM, and phase change memory. And you see this tiny STTM RAM showing up here. Looks like the STTM RAM is approaching the capabilities of SRAM and DRAM design gradually. It's not yet there, by the way. And don't take these numbers too seriously because they keep changing. Next year, you will see different numbers because STTM RAMs and SRAMs will keep improving and these numbers will keep changing. My intention is to just give you some perspective as to why SRAM is so, even with having that many transistor, that many problems, right? We still go for SRAM in everything that we use in modern electronics. Okay? They're simply the best. Let's quickly talk about one non-volatile memory which we probably all use in some form. If you have an iPhone, if you have any smartphone, chances are you have SSDs, you have flash memories. In our laptops nowadays, whichever laptop has SSD hard drive, solid state drive, they have flash memories. So here is how a flash memory works. I know you guys already know about the transistor operation, so it will be easier for me to explain. We have source and drain. We literally have a transistor, nothing else, right? We literally have a transistor. This is the gate. The difference is you have two gates here. One is floating. This is the floating gate, meaning it is not connected to any external voltage source. It is just literally, it's more like, uh, uh, here, let me just draw here. You have source and drain. You have the gate here usually, right? You have an extra gate, gate 2, gate 1 here. So here is what we do. Electrons flow from source to drain, as you know, right? When you apply voltage between source and drain, what we do is we apply a positive voltage to the gate, very high positive voltage, as you see, which attracts this electron. And this voltage is very high, by the way, very like 20 volt, as you see, right? uh, this high positive voltage attracts the electron, and they try to move towards the positive voltage source, right? But they get trapped in the floating gate. As you see, the floating gate is more like a conductor, but it's not connected to any external point. So these electrons get trapped, and you have a array of electrons just sitting there, right there. And if next time is the done, you have programmed, right? You have programmed, and this is called avalanche injection. uh, you have programmed the memory cell. How do you read? By the way, the presence of these electrons in the floating gate or absence of these electrons are used to determine 1 or 0. Say if the electrons are stored there, you can mention that this is storing 0. If the electrons are not there, you have a pristine internal gate, then say 1. So you can do either, but anyways, so you can have two states: with internal electron stored in the internal gate, without electrons stored in the internal floating gate. Okay, now that's right operation. By the way, how do you get rid of them? Again, you apply a very high negative voltage, and that repels away the charges again, and repels away the charges, and you get the previous state back. Next, how do you read from it? Let's see how to read from this cell. Imagine we have this negative. Imagine we don't have these negative charges for a while. Say, then you just have a regular transistor. You apply gate voltage, drain voltage. You notice the current. You see the amount of current that is flowing through. Then you have some added charges. I don't know if you remember, there was an expression in threshold voltage. Presence of gate charges, presence of trap charges changes the threshold voltage of a transistor significantly. So let me draw something here again. Here, this is the ID versus VGS characteristics of a transistor. This is how it looks. This is actually the threshold voltage. Okay. Now, when you have trap charges, maybe this is what you see. This is how much current you see. When you have trap, by the way, this is without trapped electrons, say. When you have trapped electrons, this threshold voltage, say, will increase all the way to here. I'm just, mm, giving you an example. So with trap. So you have, now, if you apply this much voltage, just imagine for read operation, depending on where your device is operating, you can either have a very high current, or you can have very low current, right? Depending on how you have programmed it. If you have programmed it to be here, then you have very low current for this particular voltage, say read voltage. Now, if you have programmed it to be the other thing, you will have very high current. So you can sense the difference of current, and that's how you can sense whether it's storing 0 or storing 1. And this is even a simpler example, right? Let me just draw it properly. This is IDVG, like this. This is another IDVG. This is one threshold voltage, VTH2. This is VTH1. And this is where you have the difference between the currents, right? Does that make sense? Does that make sense to you guys? Any question? No? We'll move on to a different technology right now. So if you have any question, please let me know. Okay. Now, I decided to include STT-MRAM, a brief description of STT-MRAM, because this is more like an emerging celebrity. Maybe, who knows, and within the next few years, this will become mainstream. So I wanted to be aware of this device, this memory device, like SRAM and DRAM, right? Everybody knows about SRAM and DRAM, but not everybody knows about STT-MRAM. So what STT means is spin transfer torque. So it has to do something with the spins of electrons, and we will talk about that briefly in a higher level, not going too deeper into the description. But here is how it looks. It has just one transistor and one variable resistance, and that variable resistance is made with MTJ, magnetic tunnel junction. So let me actually fast forward for a second, and we will come back to this slide. Let me fast forward to this slide and tell you how it looks like. This is the structure of an STT-MRAM. So you have a transistor which allows you to read or write or access the stored data. And you store the data here in this tiny device, which is called a magnetic tunnel junction, MTJ, magnetic tunnel junction. Okay. And this MTJ is made of multiple layers, but in a simplistic form, we can think about 3 layers. These two, FL and PL, represents free layer and pinned layer. Pinned because the magnetization of this layer doesn't really change, and free because you can change the magnetization of this layer, free layer. Okay. And depending on the relative magnetization between this free layer and pin layer, you can either have this device can present a high resistance or a low resistance. So here is what I mean. If you have parallel magnetization, just notice the arrows in the free layer and the pin layer, they are pointing in the same direction, representing they have similar parallel magnetization. That's called the P state or parallel state. And if you apply a voltage to this device, you will see low resistance or high current, right? This device will have low resistance in this scenario. On the other hand, when they have opposite or anti-parallel magnetization, we will have a high resistance state. Okay. So just by modulating or modifying the magnetization between these two layers, relative magnetization between these two layers, you can create a low resistance state or a high resistance state, which is similar to having a DRAM. You can have it charged or discharged. Charged represents 1, discharged represents 0. Similarly, low resistance represents 1, high resistance represents 0. So you have two states, you can store binary data. There you go. Now, here is how you read and write. Let's talk about read first. You apply a read voltage, say. You apply a fixed read voltage. And then that read voltage will create two different levels of current. Read. If you had a parallel MTJ, you will have a higher current because the resistance will be lower. So let's call this current as I read P. For the same voltage, V read, say, for the same voltage, if you had an anti-parallel MTJ, you would have had higher resistance. So you'll have a lower current. Let's call that I read AP. So you have two levels of currents. You can just, sense the level of current. If it is higher than a certain value, 1, lower than a certain value, 0. Done. That's how you sense. Okay. Now, how do you write? To write into the cell, you actually need bidirectional current flow. That's something unique about this cell. For writing a parallel to anti-parallel, you need to flow current from here. And that's a must. You cannot do the other way. And we will talk about, there is a slide which will talk about why that is the case. Okay. But just for now, imagine to change a parallel to anti-parallel. In other words, to change a low resistance state to high resistance state, you need to let current flow from this direction. And how do we define the direction? From pin layer towards free layer. From pin layer towards free layer. On the other hand, to do the other thing, anti-parallel to parallel, right? You need to let current flow from free layer to pin layer. That has something to do with the magnetic tunnel junction behavior. We'll talk about it. But for now, just imagine, you just need to revert the current. So you either apply right voltage here or you apply right voltage here. That's it. So you let current flow in two different directions, to right 1 or to right 0. Okay. So I hope that kind of summarizes the concept of the read and write operation of STT-MRAM and MTJ. Now let's go back and talk about the structure. We have just talked about that. I in the previous, let me just a second. Yep. So this is what I was talking about, right? This is the MTJ structure. Again, parallel magnetization, anti-parallel magnetization. And this slide will show you some materials that people often use. As you see, this is more like a ferromagnetic material. And we have an layer which I didn't talk about, by the way. There is a layer that separated free layer and pin layer. That layer is called tunneling barrier. This is usually made of magnesium oxide, okay, or tunneling oxide or tunneling barrier. And you have pin layer and free layer. And we will see what this tunneling oxide does. But anyways, this is essentially the same as we have just discussed. And here is how the switching occurs. This is the last slide about STT-MRAM. We will see how the switching actually occurs. I've already told you that to switch parallel to anti-parallel or anti-parallel to parallel, you need current flow from different directions. And here is why. The reason is the process of anti-parallel to parallel switching and parallel to anti-parallel switching occurs differently. And by the way, if you don't understand this particular slide properly, don't worry too much, because this is more like a high level overview. You will have to understand the quantum mechanics of spin to really understand the thorough detail of it, right? I'll just try to give you a high level sense, but obviously this will not really be a microscopic view. Okay. Now let's see. You have a bunch of electrons. Just notice the direction of current. The current is flowing here from this is free layer, this is pin layer, right? From free layer to pin layer, say. As you know already, wherever current flows, the electron flows in the other direction. That's how we define the convention for current flow, right? So the electrons will actually flow in the other direction here. So these are a bunch of electrons that are coming in. Let me just click here. By the way, you might already know that electrons have spins, up spin and down spin. So the yellow ones are up spin electrons and the green ones are down spin electrons. So our electrical current is actually made up of both type of spins of electrons. We just talk about electrons moving through a wire. That means current is flowing. We don't talk about all these electrons have different spins also. It's not like all of these electrons have the same spin. Okay. So here we are aware of the spins of the electron. Here is what happens next. Next, as the electrons try to flow through, I'll go back again. Just notice the pin layer has a magnetization in this direction. So whichever spin aligns well with the pin layer will be allowed to flow through easily. Okay, just imagine it like a filter. And whichever electrons have opposite spin compared to the spin direction opposite to the magnetization of the pin layer will be stuck for a while. Okay, and let's see that again. See, the yellow ones are passing through, the green ones are getting stuck. Okay, I hope that makes sense. Now let me go back again. And so yellow ones will be passing through and the green one will get stuck. But notice what the yellow ones do after passing through. This magnesium oxide is a barrier, by the way. This is just separating the pin layer and free layer. And when the yellow ones get trapped in the sorry, gets to the blue one and then gets to the red one, as you see, they get stuck and they interact with the free layer and they flip the free layer because there are too many electrons and the free layer is not really that strong of a magnet. So that electrons, this collection of electrons, actually interact with the magnetization of the free layer and flips the polarization. And that's how you change an anti-parallel, which, as you see, these arrows were pointing in the other direction. And you can change the anti-parallel to parallel. It is not possible to change the pin layer magnetization because it is a strong magnet, but it is easy to change the magnetization of the free layer because it is weaker. That's how it is designed. And let's look at it one last time. So the yellow ones are flowing, they're interacting with the free layer, and then they're flipping the free layer, they're going away. So now you have a parallel impinging from anti-parallel, right? Anti-parallel to parallel flipping. Let's see how the parallel to anti-parallel switching happens. Obviously, we will need current in the opposite direction. Here, electrical current will flow here. That means electrons will flow from here to here. Now, see, the yellow ones will pass through because they have the same magnetization. Now, green ones will again interact and change the free layer. Okay, and that's how the parallel to anti-parallel switching is done. So we, no matter what happens, we change the magnetization of the free layer, not the pin layer. The pin layer is strong magnet. We cannot change that with electron flow or something. Okay, so I hope that makes sense. Let me know if you guys have any question or anything. No?
I'm a little unsure about the second P to AP
Sure.
switching.
Sure. Okay, so I didn't really talk too much about it. Let me tell you again. All right, so you have a bunch of electrons, right? Up spin and down spin. Let's see what happens. The ones that had the same magnetization at the as the free layer. By the way, remember the difference is previously we were coming from the pin layer. Now we are going through the free layer, right? Whichever ones had parallel magnetization as the free layer will pass through. That's what you see. The yellow ones have passed through. The green ones try to pass through, but they get stuck for a while because anti-parallel magnetization and the magnetization direction of the free layer will interact with each other for a while. That's what you see. Let me see. I wish I could pause it there. Anyways, as you see, these green ones will interact and pass through. And you might have noticed that not all of the green ones will be able to pass through. Some of them will be lost. As you see, maybe out of 4, 3 passes through, 1 is lost, right? Now let me know if you have any question. I didn't really explain it then. Let me know if you have any.
Now it's clear.
Okay. All right. Okay, so let's move on to the next one. By the way, there are other interesting ideas that are on the horizon. People are talking about them. Even in STT-MRAM, it's not all rosy. It's not. There are so many good things about STT-MRAM, but there is one problem, which is the same as SRAM. The read and write operation has conflicting requirement. I'm not going to talk about it, but if you try to improve read too much, write suffers. If you want to improve write too much, read suffers. Same problem, read-write conflict. Now that you know about the presence of read-write conflict in one memory technology, it will be easier to do or examine the existence of conflicts in other memory technology as well. Okay, so because of that, people have started looking at other ideas like multi-port MRAMs, which has similar like STT-MRAM kind of structure, but it uses a different read path and write path. Don't worry too much about it. I just wanted to have these figures and show you that there are multi-port MRAMs, or MRAMs stand for magnetic RAM. Oftentimes, these STT-MRAMs are just called MRAMs or magnetic RAM. They just get rid of STT to make it simple. Okay, now, final concept that we'll cover in this lecture and in this course is a radically different array architecture, memory architecture. The reason I wanted to talk about it last is because this is the latest memory architecture that people have been working on. This is the cutting edge, and I'll give you some high level idea about this architecture, and you'll see how interesting this thing is. So this is a 3D figure. This one is the memory element, this one, and we will talk about what type of memories that you can use. By the way, as memories, you can use a magnetic tunnel junction, the one that you have just seen. There are other things like resistive RAM, phase change memories. All of this can be used as a memory here. So this is a high level memory architecture where you can use multiple types of memory cells. And these tiny little things that you see here, these are called selector, as you see, as is marked here, selector. I'll tell you about selectors later on. So all of these will be clear, don't worry. Let's quickly move to the next slide, and I'll come back to this slide later. Now, this is a 3D view. Let's think about it from a top view, right? You see, we have, there are not just four, right? It's like a 2x2 section. It could be 200 by 200. It will be a large array. This is a small portion of the array. So you have metal lines. These are metal lines. These green ones are metal lines. These red ones are also like metal lines. So you have metal interconnects flowing orthogonally, some horizontally, some vertically. There are just two levels of metals. And if you come here and see this top level view, here is what you will see. Metal lines, horizontal, metal lines, vertical, right? And in between, you have memory cells sandwiched. And ACC represents access cell. And all the other cells which are in the same row as the access cell are called half access row. They are in the row, and I'll explain half access later. And all the cells that are in the same column as the access cell are called half access column. They're in the same column, that's why column, but I will explain half access in a second. Now, here is how you access one cell. You say, imagine we want to access this particular cell. You apply the access voltage. The reason I'm calling it access is because it could be read or write. It could be write voltage or read voltage. You actually use different levels of voltages for read and write. So in general, we can just call them access voltage. So whatever the excess voltage is, you apply excess voltage to one of the metal lines, and you apply 0 to the other metal line, which is connected to the cell. So you have V access and 0. What is the total voltage appearing across the cell? Can anybody tell me? So this access is provided to one metal, 0 is provided to the other. So what is the total voltage, terminal voltage appearing across the access cell? Can anybody tell me? V access minus 0.
Yeah.
Yeah, V access, right? Simple. Now, for all the other cells, let me just draw something right here. So these are horizontal lines, these are vertical lines. I'm just, vertical and horizontal. So you want to access these particular cells, say. You apply V access to it and 0 to the other line that connects to this cell. So you have V access in total. Now, all the other columns will have V access over 2, half of V access. V access over 2, and so on, V access over 2. And all the other rows will have V access over 2. All the other rows, V access over 2, V access over 2. Now, if I ask you, what is the total voltage in this cell, this particular cell? Can somebody tell me?
0.
Yes, because both of the terminals will have the same voltage. And all of this, as you see, all of this will have 0 voltage appearing across them. So nothing will happen to these cells. Except if you see these cells, and if you try to find the cell voltage across them, you'll see that they will have a V access over 2 voltage appearing across them. All of them will have V access over 2. Same thing happens to the cells that are in the same column. We cannot just, have 0 voltage across them. It's impossible. So we will have V access over 2 across them as well. So as you see, the cells that are in the same row or in the same column will have half of the access voltage. That's why they are called half access row or half access column, HAR, HAC. Does that make sense?
Yeah.
Anybody, you guys don't have any questions at all, or? Okay, I hope you're getting it. This is called a V by 2 biasing scheme, by the way, because you use, V access over 2 or whatnot. There is another alternative to it, V over 3 biasing scheme, similar but different. So we use access and 0 for the access cell, but we use V access over 3 in all the columns and 2 V access over 3 in all the rows, as you see, right? That's a different scenario, and we will, in that scenario, unaccessed cells will not have 0 voltage, by the way. We will talk about it in a few minutes. So with that idea in mind, let's quickly move to the next cell. Right, as you see, we are again looking at the 3D view, right? This is the access cell as is shown here, access cell. This is the half access row and half access column. And as you have seen that they have some voltage, not the full voltage, but they have some voltage, half of the voltage. The cell that you're trying to read and write from, there will be current flow from them. That's true. but you don't want current to flow from the other cells that are not being accessed, right? But you don't have any choice. All of these other half access column and half access row cells will have some degree of current flow, and you cannot get rid of them. Okay, these are called leakage currents and sneak path current. Oftentimes they're called sneak path. They're sneaking out or something. Okay, so the half access column and half access row cells will have sneak path current. But the good thing is you have saved your unaccessed cells from having any sneak path current at all, because you have zero voltage across them in the V by 2 biasing scheme. But let's talk about the V by 3 biasing scheme, which we have just showed you. In V by 3 biasing scheme, you don't have zero voltage appearing across the unaccessed cell. You can try to calculate and you'll see the total voltage will be Vxs over 3. So all of these cells will have the same voltage, Vxs over 3, Vxs over 3, and Vxs over 3. So all of them will be leaking. There are some design advantages to Vxs over 3, but without going into too much detail, V over 3 scheme will have leakage through all the cells. V over 2 scheme will have leakage through only the half access row and half access column cell, but the unaccessed cells will be safe from leakage. Now, that's the final concept, by the way. Now, let me stop here. And by the way, the very first slide that we talked about, right? This will just introduce what is what. These are the memory cells. These are selectors, and I'll explain what a selector is. These are metal lines and whatnot, and it will explain what ACC means: accessed, half access row, half access column, unaccessed, right? Now, let's spend some time and talk about the specifications of a selector. Let me ask you a question now. Access cell, you are trying to access, meaning you are trying to read or write, right? But you are not trying to do anything to the other cells. But you notice that they might have some voltage appearing across them. Is there any better way to make sure that not much current flows through those cells? Is there any way to minimize the current? There will be some current, I agree, some degree of current, but is there any way to further reduce the current flow through those half access row and half access column cell? People thought about it, okay? And they figured out a way. Say, in addition to the memory cell, we will add one extra component to it. That component is called selector. These are also two terminal devices. There are different types of selector. A diode can be a selector. There are materials like phase transition material or threshold switches, vanadium dioxide, niobium dioxide. I'm not going into the specifics of it. Just imagine this is a type of device or a material which can act like a metal or an insulator selectively. Okay, it can, for certain level of voltage, it transitions into a metal and behaves like a metal. But if the voltage is lower than a certain value, it remains an insulator. So in the access cell, since you have full access voltage, that voltage will be enough to turn this selector into a metal. And it's as if it's not even there. If it is a metal, it's not even there. You just have the memory cell and you are accessing it. You are reading from it, you are writing into it, right? But when you have half of access cell, that voltage will be low enough to keep the material insulating. And then the insulator, you have an insulator in series, right? Even when you have some voltage appearing across this cell, that insulator will suppress the current, reduce the amount of current flowing through it. That's why this selector is used. The selector is a fundamental component because these memory arrays, the cross point memory array, they suffer from leakages, as you see, and there is no way to completely get rid of leakage paths. There will be some leakage paths always present. To make sure we have as low leakage as possible, we use these selectors to suppress the leakage current. And these selectors are interesting. You haven't seen these devices anywhere else, by the way. These are cutting edge. They can act like in metal or insulator depending on how much voltage you appear across them. Okay, so these are interesting. At least these are very interesting to me, by the way. I mean, this has been part of my PhD work. Okay, so in fact, these images are taken from my PhD thesis. So I just wanted to end with the cutting edge, an example of the cutting edge memory arrays that people are using. So with that, I would like to stop here and end our discussion today.